Have you ever had one of those mad scientist moments where you think, what's the absolutely craziest thing I can do with this technology? And when it comes to zero knowledge proofs or the, the verifiable computing, running the Ethereum virtual machine has kind of like often been that kind of ambitious idea. But today I'm here to present something even more ridiculous, which is to prove the execution of a real Linux system running inside a ZK proof. And yes, you heard that right. I'm going to try to actually run Linux inside ZK as improving the verification of it. So I'm using a couple of different pieces here. And let's first introduce the Cartesi machine. Probably not a lot of you are kind of familiar with it. It's an open source RISC-V emulator. RISC-V is an open instruction set. But it's not just any kind of like emulator. It's kind of like designed to be fully deterministic. It implements what's called the RV64GC ISA. And you probably might know what, in simple terms, does that actually mean. And this means basically it's a 64-bit machine that can smoothly run unmodified Ubuntu Linux, right? So, and on top of this, it can run exactly the same way all the time from the same starting point. And this is not really something quite ordinary because typically emulators run in kind of like very non-deterministic way. There's network access, etc., etc. But this is specifically meant to be a deterministic virtual machine. And the Cartesian machine in this particular case, it's not just a proof of concept. It's not something that appeared yesterday and still being developed and so on. It's been kind of in the works since 2018. It's still being developed. It's mainly C++ because Rust wasn't that popular at that time. And one of the kind of like the features of it is that every single piece of machine state resides in the memory, and you can kind of like merkleize each piece of state of the machine on a kind of like a 64-bit word level. And it's kind of persistable, as in you can pause, you can save the state, you can resume right where you started off, and even having the virtual machine itself prompting that, hey, please pause because I would like to take in some input, for example. And here's my kind of maybe a little bit bold and kind of crazy take on it. If we are looking at the future of kind of like verifiable computing or ZK applications, the optimal development target for most developers is not a specialized virtual machine. It's a general purpose processor that can comfortably run even a 64-bit operating system. So most of you probably know about a product called RISC-0, but just for good measure, RISC-0 ZKVM is kind of like the next thing we need in order to kind of like solve this problem I'm trying to solve. It's a verifiable computer. It mirrors the functions of a real embedded RISC-V microprocessor. But this is what's nice about this particular piece of product. It allows developers to write ZK proofs almost like they would code for a normal computer, as you can kind of see on the right here. It's Apache 2 licensed. It comes with a full proving and verification toolkit, both CPU and GPU. And it's also friendly to any kind of language that compiles into the RISC-V instruction set. It has 32-bit RISC-V RV32IM. It's kind of like very restricted, integer manipulation, memory access, and multiplication, and about kind of like 192 megabytes addressable RAM in the guest. One of the really nice things about RISC-0 is that they solve this kind of problem that usually you have to fit in your virtual machine, that you have to kind of fit into the amount of kind of like constraints or instructions and so on that you kind of like execute as part of one proof. But they have something called recursions, but not recursions, but continuations, where basically it allows you to split an execution across multiple proofs. One of the things they also offer is that you can kind of go from their Stark proofs into Snark proofs, kind of a little bit like Polygon ZK EVM is doing, into EVM. And they have kind of like an online service, and that's kind of like the way they're doing their business in this particular case. So our goal is we have a kind of like initial machine state, as in a machine. It contains, for example, a Linux kernel. It contains a root file system. And that state we want to transform into, well, let's say by the time it finishes, like some state Y, after undergoing certain amount of kind of like cycles of processor execution. And basically what we want to do is prove this transformation, that we actually executed this program from start to stop, or this machine state from start to stop. So the journey kind of starts with that we need to kind of like first integrate as much of the Cartesi machine code into a RISC-0 guest in this particular case. We naturally the Cartesi machine is already made for like running on top of kind of like standard POSIX systems, Linux systems, but a RISC-0 guest is more like an embedded target in this particular case. And what we want to do is that we can kind of prove at least a full cycle execution of this real bigger processor, right? So next up, we'll then try to kind of like have an external Cartesi machine that we then RPC to and kind of get memory state and the hashes and so on. So we kind of like get the initial state that we actually want to prove something. And then when the guest in this particular case is the ZK proof, just for good measure, while the host is the prover. And we then provide kind of like the memory content at this particular stage of the machine execution into the guest. So of course, next up, after you solve this, then we need to find out how many cycles of full execution can we fit into inside what's called a RISC-0 segment, as in one proof. And then kind of like over multiple iterative proofs, then we kind of like seamlessly validate that we started up the machine and it ended up holding in a particular state, and then kind of like we improve things about that state because the entire state is localized. And yeah, then also one additional thing we also need to add is that once we have kind of like made writes and modifications so on to the state, we then basically kind of like verify that kind of like we started out in a state and end up in a state, and kind of like all the memory changes that led to this new state is then actually being done. And that's something we're still working on. So something that might kind of like be second nature to an embedded Linux expert, like I used to do mobile Linux. We compile the Cartesi machine into this 32-bit ISA instead. We don't need to worry about things like the C library, the standard C++ library, or allocators, anything like that. We just need a stack, essentially, and a few helper functions, like, for example, setting memory, copying memory, and so on. And this is because the way that the Cartesi machine is designed, it doesn't require external allocation, because essentially every single piece of data or state is securely, like, they just stored in the machine's RAM or static variables in the emulator. So kind of like we took the compiled C++ code, turn it into ELF objects. Then, because we're using the Rust CC crate, it doesn't always deal very well with archives and so on. We kind of need to squish it all into one big object, and then we kind of like merge it into the Rust code of things with the CC crate. And then we have to, of course, kind of like put in a couple of like helper functions for the C++ code to access the Rust code, and in reverse, for example. So some of you might actually wonder, like, okay, so we have a 64-bit machine, right? And how are we going to fit this into a 32-bit address space, which is what the RISC-0 guest is dealing with? And I don't know how many of you have had operating system classes, but in a machine typical, there's something called let's say a translation look-aside buffer, which is basically a way for you to kind of like, when you're running inside a machine, kind of like how the CPU quickly converts between virtual and physical memory in this particular case. The Cartesi machine, because it's also an emulator, also contains a mapping between kind of like, okay, we have this physical inside the machine address. What's the offset to where it is in the actual, let's say, physical machine that we are running on? So basically, as we are then going in and encountering pages that we need as part of this proof, for example, let's say a proof over, let's say, 5,000 cycles or something like that, we only need to page in the actual memory that we're actually using during this amount of proof, and it doesn't get anywhere nearby kind of like 192 megabytes of RAM. So yeah, that's basically it. And then, of course, we'll also need to keep track of within the proof that we are actually writing some data to this, and basically we mark them as kind of like as dirty. And dirty means it's a page in the machine with updates, and then we can then commit to this in the proof, and then later on use that information to proof that we started out in a truthful state. We extracted memory from the host because we can't trust the host, and we ended up in a new state. And I'm not going to be able to show it live here, but basically it is actually possible. I'm booting up a real 64-bit Linux kernel here. It's just on a single CPU in this particular case, but it actually works. It's a little bit like trying to fit an emulator into a Commodore 64, but it works, right? And I also tested this out and working properly on GPU proving as well. So let's address the elephant in the room here. This model is far from optimized. But kind of like every innovation in the space starts somewhere. And presently, we're seeing about 2,000 to 3,000, let's say, big 64-bit RISC-V cycles for every, let's say, ZK proof. In this particular case, this is quite heavy, right? With a GPU, that basically means that on a single GPU, we can prove around 3,000 cycles in about 13 to 17 seconds. And with a Linux boot up, this means that booting up Linux itself is a task that takes around 31 million cycles. So on a single CPU, this is about 2 days. It's a bit slow, right? But there might be some use cases there where this actually matters. You can distribute this load across 64 GPUs, even separate machines, and you're down to, let's say, around 2,700 seconds instead. So kind of like future work they want to do with this, we want to kind of upstream the kind of like emulator patches we've done. We want to translate to RISC 0.17. We can start kind of like making the emulator faster and faster because we could do certain tricks, like, for example, pre-decoding the instructions, getting hints from the host about, because we can do some things in 01 time instead. You can perhaps consider making let's say a just-in-time compilation ahead of time compilation of the individual code pages, and basically getting closer and closer to kind of like how many cycles we can actually manage per proof in this particular case. And also there's kind of things like some of you might have tried on an iOS. There's an emulator called UTM, which kind of like, without having access to executable pages, you can actually get really, really considerably fast performance of an emulated machine, which you can actually potentially also use by kind of pre-compiling the most, let's say, hot areas of computation that happens during the proving. So of course, kind of like, I'm going to go with the most ridiculous thing you could potentially want to prove as in ZK. Like, for example, we can run PHP. I'm sure there will be people who want to do this. Fair enough. We can do gaming. You can basically take Doom as is, compiled for RISC-V, put it inside. You can put MongoDB inside, because who wouldn't want that? Minecraft, but also kind of like a more useful things. You can do, for example, let's say, replicating the build of a Rust compilation. For example, let's say that you actually want to verify the computation you've done. You can kind of like start doing different kind of topologies. For example, let's say, okay, I spent 3 days booting up Linux, right? Why do I need to prove that again in the future? So I kind of like go in, take this proof, modify the part of that, the memory where the root file system is sitting in, and now I'm booting up something else. One of the things we can do, which is probably going to be abused in many sorts of ways if we can prove this in practice, is that anything we can compute on this fully capable computer, we can basically potentially go ahead and prove that there's an exploit sitting in without telling people about what the exploit is. So this can be done with an emulator. So if you want to, for example, prove that there's an issue in a Linux kernel running an x86 emulator, then you can actually do this, right? And more specifically to something like the Cartesi machine, there's something where you can, for example, have some part of the execution that's public, and then you kind of like switch mode, and then some part of the execution is private, and then you continue in public mode afterwards, and kind of like stitch together, you can kind of prove that everything actually working. And so basically what's possible here is that it's kind of like adaptable, it's expansive, it's a canvas, and we're kind of like starting to paint on it now. And if you want to see some of the proof of concept code, this is something that will be evolved more in the future, but of course this is proof of concept. You can see some of these links, and you can poke me on any of these mediums. I also want to give a special thanks to one of my developers, Yeltsevita Dymchenko. She a year ago ran the first cycles of a full 64-bit machine using RVMO, which is a Rust crate, on top of RISC-0 as it was back then in October 2022. So just showing that this was actually possible. Okay, so any questions?